Okay, let's start. Hello, everyone. Thank you for being here in another machine learning launch seminar. Today, I'm really happy to host Baharan Mirzasoleiman. Baharan is an assistant professor in the computer science department at UCLA, and her research focuses on developing new methods that enable efficient and robust learning from massive data sets. Baharan received her PhD from ETH Zurich and was a postdoc at Stanford University. She was awarded an ETH medal for outstanding doctoral dissertation and a Google Anita Borg Memorial Scholarship. She was also selected as a rising star in EECS from MIT and received an NSF Career Award. So with that, Baharan, the floor is yours. Please.
Thank you so much, sir, for the nice introduction, and thank you for having me here today. So I want to talk about Coresets for efficient and machine learning from massive data sets. Whatever I'm going to talk about is a joint work with my amazing students and collaborators in UCLA, University of Washington, and Stanford University. Okay, so we all know that machine learning is becoming mainstream in lots of new and exciting applications. Here are a couple of my favorites. Personalized medicine, where we want to target treatments towards different groups of patients. Robotics, where we want the robots to kind of take care of different tasks on their own. Finance, when we want our machine learning algorithms to kind of take care of a lot of financial decisions. We have these millions of data points receiving per minute or seconds. We want to make decisions automatically. And finally, autonomous cars, when we want these cars to drive on their own among different cars, pedestrians, traffic signs, so on and so forth. And in all these applications, and in all the machine learning applications, data is the fuel for our machine learning tasks. Let me show you an example from object detection. This is from Google AI a couple of years ago. So on the x-axis, you see the number of training examples when we increase it from 10 million all the way up to 300 million. And on the y-axis, you see the performance of object detection in log scale. So as you can see, by increasing the number of training examples, we get this logarithmic improvement in the performance of this object detection task. So this clearly shows how important data is for machine learning. So larger data, the better. However, there are a couple of issues with training on very large data sets. So first, training on large data is gonna be super expensive. So let's look at some numbers. Training a single deep model GPT-3 on 45 terabytes of data. This costs $12 million. Takes more than a month to train on more than thousands of GPUs. Spends a lot of energy, like almost 20 times yearly energy consumption of the average Americans, and produces a lot of CO2, like twice driving between Earth and Moon and back. So these numbers are huge. So even if we are fine with all these numbers and all these costs, so real-world data sets are often biased. Let's look at this example of a self-driving data. The majority of data belongs to these larger classes of cars, pedestrians, and traffic signs. And only like a minority, small fraction of this data belongs to the super important class of accidents and crashes that we care the most about. And when we train our big models blindly on all this large data, what happens is that our models often perform poorly on these smaller classes. And also because there are a lot of spurious biases in these large data sets, our models cannot get good out of distribution performance. They may not generalize well on slightly different data. There are other issues that our training data sets, our large training data sets are often unlabeled, and we need to label them automatically. We use either crowdsourcing or automated labeling. And what happens is that because these processes are not perfect, we get a lot of mislabeled data in these large data sets. And we train these huge models over them. And these overparameterized models, they can easily overfit and memorize all this mislabeled data, and their performance drops significantly. And finally, because most of these large data sets we crawl from the internet or they are from user provided sources. For example, think of these large image and NLP data sets that we train our large models on. So an adversary can easily introduce a small percentage of malicious data points in these large data sets. And what happens is that these malicious data points and adversarial attacks do not even drop the performance of the model. So we do not see anything is going wrong, but what they can do is that they can change the prediction of particular data points at test time without anybody ever noticing. So these are very dangerous as well for the performance of machine learning models. Okay, so the question that I want to talk about today is that, can we select the smaller subsets of these large data sets so that we can learn from them much more efficiently and also more robust against all these mislabeled data points and adversarial attacks? Okay, so let's look at our problem formulation once again. Let's try to formulate this. So here we have the large ground set of items, let's say images. We have this ground set V on the left. This is our large data. And our goal is to find a smaller subset of this large data, S, on the right, such that when we train our machine learning model on the left data and on the right data, we get the same quality for this machine learning model. So we want this model to perform as good as on the full data, but we do not want this subset to include any noisy labels or any adversarial attacks and malicious examples. So if we can find this subset on the right that is smaller and do not contain mislabeled examples and malicious examples, we can train on this subset much faster and much more robustly. So this is the goal. This is the problem formulation. So now let's think about how we train our machine learning models, because we want to kind of address this problem a little bit more fundamentally. We are not looking for heuristics. We want to make sure that when we select this subset, this is going to work well. So let's think of the way we train our machine learning models. So we usually formulate our machine learning training and machine learning problem as follows. We have this training data V. This is our large training data of feature vectors and labels for every example. And we construct our loss function. We define a loss function per data point, and we take a sum over all these loss functions. We also often use a regularizer, and we get our final big loss function that we want to minimize. And if we can minimize this big loss function, then we get this W star, which are going to be the parameters of our trained model. And this W star is going to give us a good performing machine learning model. So this is the same formulation that we use for convex loss functions that are corresponding to traditional machine learning models like linear, logistic regression, ridge regression, and regularized support vector machine, as well as the modern machine learning models that are non-convex, like neural networks. So the same formulation we use to train all these machine learning models. How do we train this? How do we minimize our loss function? We often use some sort of incremental gradient method. For example, stochastic gradient descent, mini batch gradient descent. Our favorite type of gradient descent we usually use, which is working by subsampling one or multiple data points and moving by the negative direction of the gradient of this sample subset. So, and then because this sample, the gradient of this sample has a large variance, so we converge eventually, but this is going to be slow, especially on large data sets because of this larger variance. So here on the bottom, you see that if we get far away from the optimum, then it will take some time for us to come back and find the optimum again. So how can we find, let's think about our problem again. So imagine that we want to train our machine learning model with some sort of a gradient-based method. And we want to find this subset that let us train the same model, meaning that let us to apply our favorite type of gradient descent and converge to the same minimum. How can we do this? This is the question. So if you think about the way we minimize this loss function, the important information that we need is this notion of gradients, right? So if we can get the gradients correctly, then we are going to descend based on this gradient and we are going to find W star, right? Or we convert to some neighborhood of W star. So then now, if we want to find a subset that let us to converge to a similar W star, it means that we want a subset that has a similar gradient to the gradient of the full data, right? So if we can find a subset that has a similar gradient to the gradient of the full data, then we can apply our favorite choice of gradient descent or any gradient method, and we are going to converge to a similar W star. And similar W star means similar performing machine learning model. So let's formulate this. So here, this is going to be our problem formulation. On the left, we want to find the smallest subset. The subset is a star with the smallest size, the smallest cardinality, such that this subset satisfies the condition on the right. And this condition is that the norm of the difference between full gradients, sum of gradients of all the examples in our data, is very similar to the sum of the gradients of this subset, elements in this subset. And we can also weight each of these elements in our subset. So we want the full gradient to be similar to the sum of weighted gradient of the subset. And we want this error, this difference, to be at most epsilon. Epsilon is going to be our threshold for the error. This is the error that we can tolerate. Okay, so how can we solve this problem? I'm not going to show you more math, but I want to show you what's the solution. And the solution is intuitive, so I'm hoping you can believe me. So the solution is the following. So imagine we have our training data V. This is the feature vectors and labels of the big data that we have on the left. And imagine for a second that we can transfer all this data to the gradient space, meaning that for whatever W we are at, whatever parameters that we have, we can calculate all the gradients. So we can look at the gradients of the data points instead of their original feature vectors. Now, if we cluster these gradients, our subset S is going to be the centers of the gradients, and the weights of the subset elements would be the size of their corresponding cluster. So again, this subset is going to be the centers of the gradients on the right, and we weight each of these elements by the size of their corresponding subset, right?
Baharan, may I stop you and ask you a question here? Yeah. It seems like then it depends on F. This field depends on F, right? So the initialization of F. If I start from a different initialization, then I end up with different methods, right?
That's a great question. So I have backup the slides to answer you.
Yeah. Okay. Then
I'll. And I can answer you as well, but I can also show you slides later. So whatever I said so far is W dependent. Let me show you next slide, and then I will answer your question quickly, and then later I can also show you more slides. But this is a great point. Yes, it depends on W. So, but now, first of all, let's think of how we can find this subset in the first place, because we don't want to calculate so we want something so that we can find this subset quickly. Otherwise, if we want to spend a lot of time finding this subset, there is no point. We do not get any speed up. So how can we find this subset? So if we look at find the formulation for finding the most central examples in a large data, this is going to be our formulation. So we get this formulation is called exemplar clustering. Exemplar clustering is the same as K methods. And k-means is very similar to k-means, with the difference that in k-means, our cluster centers are average of all the data points in the cluster. In the k-means formulation, the cluster centers need to be selected from the data points. So they are the most centrally located elements in every cluster. So this is what we want to solve. And the good thing about this objective function is that it is submodular. What is submodularity? Submodularity is a natural diminishing returns property, saying that if we select an element and add it to our subset later, the benefit is less than if we select the same element and add it to our subset earlier. Because the more we select, we get more similarity in this subset. So adding more elements is less helpful later than adding them early. So this is a natural property. We have it in most of summarization applications. And the good thing about this property is that it let us solve this k-means problem very quickly with a quick greedy algorithm. So we can find this subset very quickly, condition on we have the gradients. And as Sohail mentioned properly, the gradients depend on the feature vectors. And let me talk 2 minutes about it. But if we can solve this problem, find the methods, then we get this guarantee that if we train on this subset, we converge to a very similar W star. We converge to a close neighborhood of the optimal solution W star with the same convergence rate as that of training on the full data. So let me go to my backup slides. Okay. So the answer to this question is that, so we said that we can solve this problem and find the subset, but the issue is that this subset depends on W. And if we want to find a new subset after every SGD update, then this is gonna become super slow. We don't want to do this. So what do we do instead? What we do instead is that we take this formulation, finding the most central examples. We want to solve this, and as you see, it depends on the pairwise distances between gradients of data points, I and J. Every pair of examples, we need the difference, the norm of the difference between their gradients to be able to find the most central examples in the gradient space. And these gradients are not dependent on W. So if instead of this original objective in the top, we solve this worst case objective in the bottom, which means that we look at the maximum difference, the worst case difference between gradient of I and J for all the W's. This is going to be the worst difference possible between the gradient of I and J during the training or in general in our possible parameter space. Now, if we solve this objective and have it less than epsilon, so we define new distances, worst case distances, Dij, then we can find one subset that works during the entire training. And the good thing is that finding these Dijs are possible if we have a convex loss function. So if we have a convex loss function, if we are having a traditional machine learning model, we can upper bound these worst case differences by a constant times the difference between original feature vectors. So what does it mean? It means that we can find one subset only as a pre-processing step, only from the based on feature vectors. We find the most central elements of the feature vectors. And we are done. We are going to train on this subset and we don't need to look at data anymore. But what if we have a neural network? Things become more difficult here because we do not have this nice upper bound because our loss function is non-convex. But what happens is that we can use this result from other works that are claiming that most of the variation in the gradient of the loss with respect to all the parameters in the neural network, and we have millions of parameters, most of the variation is captured by the gradient of the loss with respect to the input to the last layer of the neural network. And if we think of, let's say, classification algorithm where we have softmax cross entropy in the end, then this gradient with respect to the last layer, we can get it with a forward pass. So we do one forward pass, we get that gradient of the last layer, and we find the central elements only based on this gradient of the last layer, which is going to be much lower dimensional. For example, the dimensionality of the number of classes. So if you have C410, then we map every data point to a 10-dimensional vector, and we find the central examples there. Of course, we cannot get rid of the dependence to W, so we have to update our subset every now and then, every epoch or every couple of epochs. But at least we can find the subset quick. Okay, so let me show you some experiments. So first of all, the reminder, what is the algorithm? If you have a convex function, you can think of this as feature vectors. If you have neural network, you can think of this as last layer gradients. So we use a quick greedy algorithm, a fast greedy algorithm, to find the central examples, either from the feature vector space or from the gradient space. We weight every data, every selected example with the size of its corresponding cluster, and we do weighted gradient descent, weighted incremental gradient descent, weighted stochastic gradient descent. And by weight, I mean we just multiply the size of the cluster by the learning rate for that particular data. So we do this either once for convex function or iteratively for non-convex functions during the training. And this is going to be our algorithm, which I showed you the guarantees for in the previous slide. So let's look at examples. Let's start with convex functions. So here we are training on this IJCNN data. This is a logistic regression function. And this data set is super imbalanced, 9:1, if I remember correctly, imbalance ratio. And you can see on the y-axis training loss, and on the x-axis time, including the time to find the subset. So you can see this orange dot in the bottom right, which is SGD applied to all the data. There is no subset here. This is normal training. And you can see if we train on random subsets of size 10% all the way up to 90%, we cannot even get close to training on full data because the data set is very imbalanced. But if we do SGD, we apply SGD on these subsets that we find based on this centrality idea. And this is convex, so the examples are found once based on the feature vectors. Only after selecting a subset of size 30%, we get the same solution as that of training on the entire data, but we get 7 times the speed up. Let's look at like a neural network, but a small one. So this is MNIST. This is a small neural network 2-layer. So left plot, you will see the test accuracy versus time. And here we are finding a subset at every epoch. On the right, you see the training loss. And this orange line is SGD on the full data. This blue line is SGD on these subsets that we find, a new subset at the beginning of every epoch. And this green is SGD applied to random subsets of the same size. And here again, we got 2 to 3 times the speed up, and this is a smaller model. For deeper models, what we found is that we can also incorporate the curvature, and we can precondition the gradients to the curvature to kind of do better. And here you see that for this 2 ResNet 50, which is much larger, and ResNet 18, CFAR 100 and BDD, I'm showing you here, we also get a good speed up by only training on these subsets. Again, we update them every epoch or every couple of epochs. And we get a speed up versus training on random data sets and also full data sets. Okay. So let me also show you this final plot, and I wrap up the things here on this part. So here, I also mentioned that these large data sets, because they have a lot of redundancies and spurious correlations, so they do not generalize, our model may not generalize well on slightly different data. So I just want to say that these subsets that we select, because they have less redundancy, we try to kind of select one example per cluster of similar items. So on the top, you see in distribution performance on different data sets. On the bottom, you see out of distribution performance on a slightly different corrupted version of CFAR10 and CFAR10C, which is corrupted with noise and blurring and other stuff. And you see that we also get a better performance on out of distribution examples like OOD performance. So getting rid of redundancies is good both for efficiency and also improving OOD. Okay. So final comment here is that we can use similar ideas to also select the most effective data points for data augmentation. So if we think of weak data augmentation, which is a standard data augmentation we use when we train CFAR10 with ResNet. So this is cheap, this is quick. We replace the items with the augmented version of them. But SOTA data augmentation methods, they can be very, very expensive because for a single data point, they generate multiple augmented versions and they append the data with these augmented versions. So finding the most effective augmentations a lot of times is very expensive, and appending the data with multiple augmented items can increase the kind of training time from 3x all the way up to 13x. So I should fix this slide. All the way up to 13x. But we can use a similar idea to find the data points that are most effective to be strongly augmented, so that we can only generate these expensive augmentations for these data points and append them to the data. If we do this, we see that we can do much better than augmenting random subsets, and we can kind of augment these data points when we only train on Coresets. When we train on random data, we can augment these elements, they are super helpful. And also when we train on full data, we can also augment these elements and only add these extra augmentations to the data. And this is also improving the performance. Okay, let's kind of wrap up our discussion about efficiency. Let's switch gear to robustness. And what I want to show you is that similar framework, similar idea, also let us train more robustly. So why is that? So if you remember, the other issue that we had is that in real data sets, we often have a lot of noisy labels. And these noisy labels, we want to get rid of them because otherwise we overfit to them and the performance drops. And again, I want to show that similar framework we can use to also gain robustness. Let's start with noisy labels. So again, starting with our problem formulation, let's assume that we have a simple square loss because it's simpler to analyze. And we want to train a deep network with gradient descent. And again, because this is simpler to analyze, but in practice and in the experiments, we have cross entropy, we use mini-batch gradient descent and all those algorithms. But let's look at the gradient descent formulation. The gradient, we can decompose it into two terms. This is a deep network. The first term is the Jacobian. This Jacobian is the partial derivatives of the network F with respect to all the parameters for all the data points. So this is a huge, huge matrix because we have millions of data points, we have thousands of data points, millions of parameters and thousands or millions of data points. This is huge. The second term is the residual, which is the difference between the prediction of the network and the labels of the data. Okay, so this Jacobian, we cannot even calculate probably because we will get out of memory error, but this has some nice properties. So the properties, the important properties is that if we do SVD on this huge Jacobian matrix, we see that the Jacobian matrix of usual neural networks, this is an example of a ResNet 32, is very low rank, meaning that we have this dotted area that has a smaller number of large singular values. And the rest of this histogram on the left, you see that we have millions of very small singular values. So what does it mean? So it means that we have this lower dimensional space, which is important for learning. And we have this super high dimensional space, which is non-important for learning. And when we train our neural networks, what happens is that we learn very quickly over this important green area corresponding to larger singular values. And we learn very slowly over this reddish area, which is very high dimensional, non-important. And all the overfitting and bad stuff happens over the red area. So there is another property that we can also observe, that all these clean labels, the data points have good labels, their residual and their label, when we multiply it by the Jacobian to calculate the gradient, they have a very good alignment with the green area. And most of the bad labels and mislabeled examples, their residual have a good alignment with the red area. Okay, so now thinking about this, in lower dimensional space, things are closer to each other. In higher dimensional space, things spread out. In terms, like, think about millions of dimensions that we have, nothing is close to each other. Now, clean data points fall in a lower dimensional area, lie on a lower dimensional area. So the similar clean data points, they cluster together in the gradient space. We are talking about the multiplication of the Jacobian with the residual. Good data points fall on this lower dimensional space. Similar good data points cluster together. Mislabeled examples fall on this huge dimensional space. They spread out all over the place. Bad data points, mislabeled data points do not end up close. And what happens is that, again, if we look at the centers of the gradient space, because the clean data points cluster together, we can find most of the clean data points. And we do not select mislabeled examples. Okay. And this was exactly the algorithm and the framework that we talked about in the first part. So we can guarantee that if we train on the most central gradients, examples that have most central gradients during the training, we can avoid all these mislabeled examples and we get robustness guarantees. And let's look at whether this happens in practice or not. So here I'm showing you training training a ResNet on CFAR 10. Here we have 50% noisy labels, or 50% of the labels are flipped to other classes. And I am showing you selecting subsets of size 30%, 50%, and 70%. If you remember, for neural network, we update the subsets, let's say, every epoch. So x-axis is during the training. Y-axis is what is the fraction of correct labels in the subsets that we select. And as you see, as we keep training, our subsets include, like, most of the elements in the subsets have clean labels. So these central gradient elements examples that we select, they have good labels. They are safe to train on. And if we select 30% or 50% examples, you see that over time, we can almost find all the good examples. And obviously, if we select 70% of the data, because 50% is mislabeled, we are going to have noisy labels as well. But what we observed is that for different fractions of noisy labels, if we select subset size 50% during the training, we are going to be safe. So let's look at numbers. Again, training ResNet on CFAR, comparing to all the other baselines for training with noisy labels, robust training methods, you see that we can get a very good kind of test accuracy for CFAR 10 and 100, different fractions of symmetric and asymmetric noise, up to 80% noise, symmetric and 40% noise asymmetric. And we get a very good test accuracy, robustness. And I had one more experiment. I think I skipped, but that is fine. I will show you later. Okay, so far so good. But what if we have even more noise? Like if you look at here, if you look at the 80% noise column, so things are not working super well there for none of these methods. We get a good test accuracy and robustness. And what if we have more than 40% asymmetric noise? Or what if we are talking about CFAR 100, where things are more difficult to deal with? So can we improve this further? And the short answer is yes. So if you think of what we were doing, we were selecting the central gradient examples, right? And when we have too much noise, the network cannot learn anything from the beginning. Like our gradients become very random. So selecting the central elements is not going to be super meaningful. So we somehow need a way to let the network train a little bit such that we can trust our gradients, and then we select the central examples. So how can we do this? The idea is that let's get rid of all labels in the beginning. If we suspect that we are going to have even more noise, this data set is even more noisy in terms of the labels, we can get rid of all the labels. We can train unsupervised for a while. For that, for example, we can use contrastive learning. So contrastive learning generates augmentations for all the data, for all the examples in our data. And it tries to kind of make the representation of similar augmentations for the same data point close and push away the representations of augmented examples corresponding to different data. So we maximize the agreement between different augmented versions of the same example and minimize agreement between different augmented versions of different examples. And we only learn the representations. There is no label. Okay, so if we do this first, train a little bit unsupervised, let's say with contrastive learning, we get these representations from our neural network. Then we train a linear classifier on the representations that we learned and all the noisy labels that we have. This is just a linear classification, training that. Then we get a very good robustness against noisy labels. Why is that? The reason is that here we showed when you do this contrastive learning unsupervised as a pre-training, what happens is that if you look at the Jacobian, or if you look at the representation matrix that you learn, which is the Jacobian of this linear classifier that you train with the labels, this representation matrix is very low rank, becomes very low rank, meaning, and it has one large singular value for every subclass in your data, and the rest of the singular values become very small. So if you look at this plot, we are comparing in orange a randomly initialized network, the representations of that, with a pre-trained network, represent a singular SVD of the representations of that in blue. And as you see, the blue one is very low rank compared to the orange one. The other property that we get is that this left plot is what I showed you in the previous slide. In the right plot, you see that the good labels of every subclass align very well with the large singular value vector corresponding to that class, to that subclass. So for every subclass in the data, we learn one important directions which align well with the good labels of that subclass. And the mislabeled examples align with this smaller kind of singular value vectors, which are not doing much. So as a result, pre-training provably improved the robustness to noisy labels. Here you see these small singular values and no alignment with the good labels. And what happens is that we can prove that this is going to improve the robustness. But when we train, so when we train this linear classifier after pre-training with all the noisy labels, we can still use our subset selection method that I explained. Like we can still select the central gradient examples. Now the pre-training ensures that we have good gradients. So we can easily discard the mislabeled examples by only sticking to the most central gradient examples in this downstream task of training this linear layer. So combination of both pre-training plus selecting central examples let us to train much better on a lot of noise. Now let's look at CFAR10. The performance improved from, I don't know, 50% to almost 80%. And also on CFAR 100 asymmetric noise, this gives us a lot of boost in the performance when we have a lot of noise. Okay, so this is the web vision. This is a real noisy data set. Again, same happens. Okay. So I want to talk a little bit now, switch gears, talk a little bit about malicious examples, and I will wrap things up here. So I wait 10 seconds if there's a question, otherwise I can continue with this. Okay, let me continue because we don't have much time. So let's talk about the last issue, robustness against adversarial examples, in particular data poisoning attacks. Let's remind ourselves of the setup first. Here, an adversary can add a small fraction of malicious examples to the data such that the performance of some data points at test time changes. And what I want to show you again is that same framework that we talked about that is good for efficiency and also robustness against noisy examples is also helpful to get robustness against targeted attacks and adversarial examples. Why is that? So again, let's start with the problem formulation, how the attacks are generated, in particular data poisoning attacks are generated. So the goal of the adversary is to change a little bit, let's say a small fraction of data points in the data, something around 1% of data points, in a way that when we train on the data on the right, you see the training loss, and this xi plus delta, so the adversary is going to add a noise vector to this 1% of the training data points. This noise vector is very small, such that we look at the examples, we see nothing is changed, such that they are invisible. But what happens is that when we minimize our training loss on the right, we also minimize an adversarial loss on the left. The adversarial loss is misclassification of an example in test time. So adversarial loss, xt is a test time example on the left, and y adversarial is mislabeled version of xt. We want to intentionally change the prediction of this test time data xt at test time by minimizing a training loss on perturbed versions of the original example, and this perturbation is small and only for 1% of the data. So the adversary wants to basically find this perturbation that this thing happens. What is the intuition? Let's look at the visualization. So here, this blue is the target class, and this green is the poison class, meaning that this adversary wants to change and add a little bit noise to 1% of the data in the green class, such that this black star is the data point that we want to change the prediction for. This is test data. This is not included in the training data. But when we train on this training data over time, these are the poisons. These poisons are the noisy data points. When we train on this poison data, the representation of the target moves from the blue class towards the green class. As a result, when we see this star at test time, we classify it as green instead of blue. We want this, like adversary want this to happen. So how can the adversary solve this problem? So again, we want minimizing the training loss to minimize the adversarial loss. So if the gradient of the training loss is similar to the gradient of the adversarial loss, by minimizing the training loss, we are also minimizing the adversarial loss. So state-of-the-art data poisoning attacks work by matching the gradient. So they kind of want to optimize this noise to be added to 1% of the data points, such that the gradient of the training examples is similar to gradient of the adversarial loss. And so they generate these malicious data points, noise vectors, by optimizing the objective in the bottom. Okay. So they optimize for this, but we want to deal with this. Like, we want to kind of defend against this. So what we observed is that this 1% of the data points, adversary is selecting at random. And then it optimized for the noise to be added to this 1% such that the gradients match. The gradient of training match the gradient of the adversarial loss. So what we observed is that for this 1% of the examples, most of them, optimizing this objective in the bottom doesn't work. So for most of them, we cannot optimize this. And we call these data points ineffective poison, and we color them in purple here. Only for a small fraction of this 1%, the adversary can successfully match the gradient of the adversarial loss by adding random perturbations. So we call this effective poisons. We call this successful kind of data points. We call them effective poisons. And if we get rid of all the ineffective poisons, the attack is still gonna be successful because of the red ones. But if we remove the red ones, even if we have all the purples, the attack doesn't work. So we only care about effective poisons. And we want to get rid of them. So what we observed is that the gradient of these effective poisons is not similar to each other first, and is not similar to rest of the data points as well, because they are anomalies kind of. Ineffective poisons, they are similar to each other, and they remain similar to the rest of the data points as well in terms of the gradients. So these effective poisons that we care about and we want to drop from the data, these are, again, becomes isolated in the gradient space. They become anomalies in the gradient space, and they separate from the rest of the data, in particular earlier in training. So we use the same framework. We cluster our gradients, but now we drop clusters of size 1 in the gradient space. And as you see, this cluster size, this is the cluster size that you see in these plots. So most of the clusters of size 1 are red. They are effective poisons, and ineffective poisons and clean data points are making larger clusters. So if during the training we get rid of clusters of size 1, we do not harm the training. This is the gradient of the, so this plot shows that the distance to the full gradient for our method in red is smaller to distance to the full gradient for a random subset of examples, meaning that we will have a similar gradient. We do not harm the training much. But what happens is that we can successfully drop the effective poisons, and without harming the accuracy, we can drop the success of various types of data poisoning attacks quite a lot. At the same time, we know that we have our efficiency kind of benefit from the previous parts of the talk. So we can defend very successfully against data poisoning, very efficient. So I'm done here, and I'm hoping that I could convince you a little bit that less data can be even more for machine learning, and let's try to kind of go smaller but higher quality. Thank you very much.
Thank you so much, Baharan. Let's unmute and thank our speaker.
Thank you.
Questions?
Okay, so I guess I can jump in and ask the first question here. So, in this the last work that you just presented, so I was wondering here that this kind of ratio of the ineffective to effective, how related that is to the allowed perturbation that you're having?
Okay, so that's a good question. So what we observe is that these attacks, I had some slides on that, so I'm not sure if I have it here. So here, if you look at this part, so the ratio is mainly kind of determined more than the perturbation bound by the setting of the training. So in particular, when we train from scratch, we have much smaller percentage of effective to ineffective poisons. But during transfer learning, we have a much larger fraction of effective to ineffective poisons. And the reason is that here, gradient matching is much easier to solve. But even in this case, that we have almost 80% effective poisons, the same thing happens, that these poisons scatter. These successful effective poisons scatter, and I can give you kind of an intuition about it. So for the effective poisons, you can imagine that we start optimizing from this class towards the other class. So the gradient, we change it from a gradient that is similar to this class, and we modify it so that it matches the gradient of data points in another class. And you can imagine that this is not a similar pattern that is happening during the training for examples of this class. So even when the ratio of effective poisons are high, they still become distinguished from the rest of the good examples in their class. And because 80% of 1% is still 1% is still smaller than 1%, so they become distinguished and separated from the rest of the clean examples in that class. So still we can get rid of them.
Okay, makes sense. Thanks.
Sure.
So I have a piggyback question on that. So actually two things. First, when we say gradient, because these are neural networks, I'm assuming that we are still talking about the last layer.
Yes, yes.
So, I mean, have you guys looked into what will happen if you do the two last layers or the just the connected layers? And that's one question. And then the second question is, the robustness to adversarial attacks. Is there an assumption that the attacker is oblivious to the defense mechanism? Or in another word, would it be possible to design adversarial attacks that cluster together in the gradient?
That's a good question. That's a good question. So for the first question, we look here, whatever I showed is the last layer. For the efficiency part, we looked at the last two layers. It is helpful to some extent. It is not changing the story, but it can help a little bit. But if we go more than last two layers, because the dimensionality becomes large, clustering becomes more lower quality. Like clustering becomes less meaningful and more difficult. As a result, like going more than last two layers is not gonna work well anymore. So it's a very good question, but open question. How can we find better gradient estimates than last layer or last two layers? And so one potential answer is that we can do network pruning, find the most important weights, look at the gradients only with respect to those. But the issue is that if we want to, let's say, calculate the gradient with respect to the most important weights, we have to, if those weights are in shallower layers, we have to do backprop. And backprop is the expensive part of training. So it is not gonna give us a speed up, most probably that much. So that would be the downside. So if we can do something with the kind of later layers, if we can improve that, that would be helpful. But I don't know what would be the answer. So for the second question, that is also a very good question. So the question is that if the adversary knows that we are going to employ this attack, can they do better? So first of all, if the adversary makes this constraint that I want to generate clustered poisons, it has to add this constraint during this gradient matching step. And this gradient matching step is itself not super easily optimized. And if you add another constraint into it, the quality of the poisons would be lower. Imagine that you take 1% random data. This 1% data do not have similar gradients. They are having very different trajectories to match the gradient of the target. Now you want to cluster them. So it is not gonna work. Like the poisons will be lower quality. The other way we can address this is that how to select an initial 1% data points that can get you clustered gradients, like clustered trajectories to matching the target. And that is a good question that currently there is no solution for. So imposing constraint on this is not gonna work well, but maybe somebody can select in a smarter way this initial random data points such that their gradient cluster together. And because of the very non-convex nature of the loss, it is going to be very difficult to solve. And currently there is no solution for it. So because what you can use is the gradients of these data points at the beginning, let's say based on a trained model, but the gradients change a lot during the training. So you can optimize for a part of it, but the rest may not follow. So it's gonna be tricky, but it's a good question.
Thank you.
Sure.
Any other questions? Okay.
I guess I
Last
can
call.
ask a question on the first work. So I think at one point you mentioned like a 9-to-1 imbalance. I don't remember which data set. Okay. And so the one thing I was thinking here is that, so I assume that these were looking at things like accuracy as the metric.
This is the training loss residual, meaning that what's the distance to the optimal solution, because this is a convex setting.
Yeah.
The accuracies we also looked at, we have in the paper.
Because I guess I was wondering then if we're approximating the full data set, that if we were to look at like per class performance of something like F1 macro, for example, that would this be alleviating any of these imbalance issues within the data, or especially if we're applying these the weights to the samples as well, that I was wondering if there could be variance.
Okay, I think this is a great question. So I think the difference here between what we do and the random subsets is that, so theoretically, the gradients of different classes cannot be similar because the label is included in the gradient calculation. Because of that, we select subsets from classes separately. We do not mix all the data points and then select a subset. We select a subset from this class, that class, and we can do this in parallel because these are independent. And now what happens is that if we want to match the training on the full data, when we select a subset, we keep the ratio of the classes, meaning that from the small class, we select 10%, and from the larger class, we select 90%, and then we merge them, right? And as a result, comparing to random, we are sure that we are not gonna miss the small class, but because we want to match the full training, then we keep the ratio. But if you want to do better on the smaller class, you can very well select more from the smaller class and select less from the larger class. Or if you want to really get rid of the redundancies in the data, you can sparsify the larger gradient clusters, which is something we are working on right now. And that would be very helpful for OOD because you prevent the network to memorize these spurious correlations because of the redundancy. So a lot of times, same combinations happens a lot in your data. For example, thinking about the images, like you always look at the bird at the sky background. And if this happens a lot, you get correct prediction, but because of the sky, not because of the bird. But if you sparsify, if you prune some of these bird and the sky images, then there is a much better chance that your network learns the bird, not the background. And we can do this very well based on these gradient clusters, because otherwise finding the similarities would be heuristic. And current experiments are showing that this is actually helpful for improving the OOD performance.
Thank you.
Sure.
So one more question, Baharan, at some point you mentioned the Hessian normalized version helps, right? Like the inverse of Hessian times the gradient helps.
Yeah.
I mean,
so
I
here again,
help,
the Hessian
right?
and everything is lastly.
Got
Yes.
it. But I mean, it always helps, right? Like
Yes.
if you had the actual gradient, this should help, right? But like the fact that it helps only when it's calculated on the last layer is kind of interesting. Right? Like,
Yes. So the last layer. So we also tried at some point, I think, the first layer and compared it to last layer. Again, the advantage is that last layer is much faster to get information for, and it is, at least empirically, seems to be the most informative. So theoretically, I do not have a good answer, but practically it's working better than the rest of the layers. Although some people that are experts in vision or NLP, they say that for this particular task, this layer might be more informative. For that particular task, this other layer might be more informative, and very well you can calculate the gradient with respect to that layer.
right. Yeah, I mean, even in continual learning, right? Like there are approaches that estimate the importance of parameters and then regularize the changes on those importance parameters. And if you look at the histogram of importance parameters as a function of layers, the last layer has the highest importance often. Like there are many papers that show this over.
And interesting, for a softmax cross entropy, that gradient with respect to the last layer is just the logics minus the label. So we are working a lot with the predictions, the logic bit.
Fantastic. So if there is a final question, it's time to ask now. Okay, if not, let's thank Baharan one more time. Baharan, thank you so much. This was a wonderful, wonderful talk. We really appreciate your time.
Thank you very much. Great talking to all of you today.
Thank you.
Bye.